is differentiation? Differentiation is indeed a fundamental concept in calculus. It allows us to find the rate of change of a function with respect to one of its variables. For example, the context of motion, differentiation helps us find instantaneous velocity by differentiating the displacement function with respect to time. Anti-integration, which is also known as integration, is the reverse process of differentiation. It involves finding a function whose derivative is a given function. Integration and differentiation are closely related, forming the basis of calculus and enabling us to solve a wide range of problems in physics, engineering, economics, and many other fields.
So, basically, the differentiation have many applications such as related weights, analysis of function 1, which is we found out the maximum and minimum point, concavity and inflation point, also sketch the graph. Next, analysis of function 2 is the same with analysis of function 1, which is we found out x and y-intercept, horizontal and vertical asymptotes, and also sketch the graph. Besides, rho theorem and mean value theorem, and the last one is applied maximum and minimum problem that we will discuss and use it to solve the problem in this video.
So, in this part, we're gonna talk about what is maximum and minimum problem. The maximum and minimum problem is the process of finding the maximum and minimum value is called optimization. Many applications problems in calculus involve function to find maximum or minimum value.
So, why we use maximum and minimum? Absolutely, you are describing optimization problems in calculus, which are common in real-world applications. These problems involve finding maximum or minimum values of a quantity like volume, cost, time, and others. Here's a breakdown of how this problem typically unfolds. Say that you are given a situation that requires maximizing or minimizing something. For example, finding the maximum volume of a box, minimizing travel time, or minimizing cost. This function represents what you want to optimize, maximize, or minimize. It's usually given directly or can be formulated based on the problem description. For instance, if you want to maximize volume, the volume function of the box would be your objective function. These are conditions or limitations that must be satisfied. Constraints could be restrictions on dimensions, budget limits, time constraints, and others. For example, the dimension of the box may need to fit within certain limits to be accepted by the post office. For formulating the optimization problem, we combine the objective function and constraints to form a mathematical expression that represents the entire problem. This often involves setting up equations or inequalities based on the given information. Then, we use calculus techniques, particularly differentiations, to find critical point where the derivative of the objective function is 0 or undefined. These critical points may include potential maximum or minimum values of the objective function. Once critical points are identified, we check whether they satisfy all the constraints given in the problem. Sometimes this might involve using additional methods like Lagrange multipliers for constraint optimization. Finally, interpret the result in the context of the original problem. We determine the maximum or minimum value of the quantity of interest and ensure it satisfies all given constraints. This step illustrates how calculus, specifically differentiation and sometimes integration, is used to solve real-world optimization problems. By understanding the relationship between variables and how they interact under constraints, we can efficiently find optimal solutions to a wide range of practical problems.
Now, we're gonna explain about how to solve the maximum and minimum problem. First one is we have to make sure to understand the problem by identifying the function and the domain. Next, find the critical points. Make sure to let the derivative equal to 0 and find the values of the variables. And for the last one, classify critical points. If the second derivative is less than 0, it is a minimum value, but when it's more than 0, it is a maximum value. This is our problem statement where Anya is planning to serve watermelon juice to her visitors in a cylindrical container. The volume of the container is 360 cm3. If the cylindrical container has a radius of r cm and a height of h cm, including top and base, let A be the surface area. From the problem statement, we found out there are 4 questions for us to solve. So, this is the first question, where the question asks us to express h in terms of r. In this question, we're gonna use the formula for volume, which is V equals to pi r square h. In that problem statement was stated about the volume of container, which is 360 cm3. In this question, they want us to express h in terms of r. So our final answer would be h equals to 360 over pi r square.
Question 2. Show the surface area A for the tank is A equal to 2 pi r square plus 720 over r. We know that the surface area of cylinder is 2 pi r square plus 2 pi r h. H is 360 over pi r square that we got in the previous question. So, just substitute the value of h into the h of the surface area of the cylinder, and we got the answer is 2 pi r square plus 720 over r. The answer is shown. Question 3. Find the radius that will minimize the surface area of the cylindrical container. Give the answer correct to 2 decimal places. Firstly, to find the radius, we need to find the derivative from the equation that we got in the previous question. From the surface area, which is 2 pi r square plus 720 over r, differentiate the equation, and the answer is 4 pi r minus 720 over r squared. Next, to find the radius, we need to let the derivative equal to 0 to find the values of variables. Let r in terms of cube root of 57.296. Thus, we will get the value of r, which is 3.86 cm. Next, use second derivative to prove the value is minimum or maximum value. From the second derivative, we get 4 pi plus 1440 over r cubed. Substitute r equal to 3.855 to the equation. From this second derivative, the r is a minimum value because the value is greater than 0, which is 37.70. Therefore, r equal to 3.86 cm will minimize the surface area of the cylindrical container. For question 4, find the minimum surface area of the cylindrical container. We know that from the surface area, A equal to 2 pi r square plus 720 over r. So, just substitute the value of r, which is 3.86, and we will get the answer is 280.15 cm square.
In summary, maximum and minimum applications, which are a component of differentiation application, are highly helpful in our day-to-day life, especially when it comes to involving business or other challenges that requiring a calculation. For example, from the application of applied maximum and minimum problem, we get to know how to get the answer that related to life, such as radius of object and many more. Indirectly, we can solve the problems easily, simply, and concisely. Therefore, by applying the right formula, which is first and second derivative, we will get an accurate answer. This proves that there is no word that can describe how important is the application of differentiation in our life.